Our cosmic quest. What is physics? What is physics, you ask? It's a fantastic question. Physics is the ultimate adventure. It's the science of everything from the tiniest quark, so small you can't imagine, to the biggest supercluster of galaxies, stretching across billions of light years. Physics tries to understand it all. It's about asking, how does the universe work? What are the rules? It's a grand cosmic detective story, and we are all invited to play. Physics is the bedrock, the foundation for other sciences. Chemistry, that's physics in action. How atoms bond, how molecules dance. Biology, that's complex chemistry, which is complex physics. Engineering, that's applying physics to build amazing things. Bridges, spaceships, smartphones. Physics gives us the tools to understand and to create. It is the language the universe speaks, and we are learning to become fluent. Why bother with physics? Because we are curious. It's in our DNA. We look up at the stars. We wonder, how did they get there? What are they made of? We see a rainbow. We ask, how is that beautiful arc formed? Physics provides the answers, or at least it guides us, on the path to finding them. It fuels our imagination. It expands our cosmic perspective. It reminds us we are part of something vast, something truly magnificent. Think of physics like this. Imagine the universe is a giant, intricate machine, a cosmic clockwork full of gears and springs, all working together in ways both simple and profound. Physics is our attempt to find the instruction manual, to read how it all operates, to understand the principles that govern every movement, every change, every phenomenon, from a falling apple to an exploding star. It's a quest for ultimate understanding, a journey that never ends. The apple and the moon, Newton's dance of motion. Let's talk about motion, how things move, or why they stay still. Our guide here is a giant, Sir Isaac Newton. You've probably heard of him. The story goes, an apple fell, bonked him on the head. Maybe, maybe not, but it got him thinking about gravity and about motion. His ideas changed everything. They gave us the laws of classical mechanics, rules for how everyday objects behave. These rules are still incredibly useful today. Newton's first law of motion. This one is all about inertia. Inertia is a cool word. It means objects are lazy. In a way, they like to keep doing whatever they are already doing. If an object is at rest, it wants to stay at rest. Like your cat napping in a sunbeam, it won't move unless something makes it. If an object is moving, it wants to keep moving in a straight line, at a constant speed, forever, unless a force acts on it. Think about riding in a car. When the car suddenly stops, your body lurches forward. Why? Inertia. Your body wants to keep moving because it's moving. Seatbelts are a great invention. They fight inertia. They apply a force to stop you safely. Or when the car speeds up, you feel pressed into your seat. Your body wants to stay put, but the car is pushing you forward. That's inertia again. It's everywhere, all the time. Imagine a hockey puck, sliding on perfectly smooth ice, no friction at all. If you give it a push, it will glide on and on. It won't slow down. It won't turn, unless something hits it, or air resistance pushes against it. In the vacuum of space, a spaceship can turn off its engines and just coast for millions of miles, because there's almost nothing to stop it. Newton's first law, simple, yet so powerful. It's the universe's way of saying, don't bother me unless you have to. Force, mass, and a little push. Newton's second and third laws. Newton didn't stop with just one law. Oh no, he gave us more. His second law is super famous. You might have seen it. F equals sign ma. Force equals mass times acceleration. Let's break that down. Force is a push or a pull. Mass is how much stuff an object has. Its heft. Acceleration is how quickly an object's speed changes, or its direction. So, the more force you apply, the more an object accelerates. Makes sense, right? Push harder, it goes faster, quicker. Now let's consider mass. Them in F equals sign ma. If an object has more mass, it's harder to get it moving, it has more inertia. Imagine pushing a toy car, easy peasy. Now try pushing a real car, much harder. You need a lot more force to get the same acceleration, or if you apply the same force to a bowling ball and a baseball, the baseball will fly off much faster because it has less mass. The second law explains all this. It's a recipe for motion. Then comes Newton's third law. This one is about teamwork, or cosmic give and take. For every action there is an equal and opposite reaction. Sounds simple, but it's profound. When you push on a wall, the wall pushes back on you with the same force. You don't see the wall move because it's big and heavy, but you feel its push. If you're on roller skates and you push that wall, you'll roll backwards. The wall pushed you. Think about a rocket blasting off into space. How does it go up? It throws hot gas downwards. Violently, that's the action. the gas pushing down. The reaction? The gas pushes the rocket upwards, with equal force. That's what lifts it, or when you jump, you push down on the ground pushes back up on you, launching you into the air. Even walking works this way, you push back on the floor pushes you forward. Newton's laws, they are everywhere, governing every interaction. Sparks and shocks the electric universe around us. Let's switch gears, from motion to something invisible, but incredibly powerful, electricity. We use it every single second to light our homes, to power our gadgets, to connect with the world. But what is it? At its heart, electricity is about charge. Tiny particles, called electrons and protons, they carry electric charge. Electrons have a negative charge. Protons have a positive charge. It's like they have tiny little labels. Plus or minus, these charges interact in a very specific way, like charges repel each other. Two negatives, they push apart. Two positives, same thing, they don't want to be near each other. But opposite charges attract. A positive and a negative, they pull towards each other, like tiny dancers seeking a partner. This attraction and repulsion, this is the electric force. It's one of the fundamental forces. That runs the universe. It's what holds atoms together. It's what makes chemistry happen. Think about static electricity. On a dry day, you walk across a carpet, in your socks. Then you touch a doorknob. Zap, you get a little shock. What happened? As you walked, you scraped electrons off the carpet, or onto it. So your body built up an imbalance of charge. Either too many electrons, or too few. When you touch the metal doorknob, the charges jumped. To even things out, that little spark, that was electricity in action. Tiny charges on the move. Electricity usually flows through materials called conductors, like copper wires. The electrons can move easily through these materials. This flow of charge is called an electric current. It's like water flowing in a pipe, but instead of water molecules, it's tiny charged particles. This current is what powers your toaster, your phone, your computer, an invisible river of energy, flowing all around us, harnessed by human ingenuity to make our lives brighter and more connected. Section 5. Invisible Forces, the Magic of Magnetism. Now for another invisible marvel, magnetism. We've all played with magnets, those fascinating objects that stick to your fridge or pick up paper clips. What's their secret? Magnets create an invisible area of influence around themselves called a magnetic field. You can't see it, but you can see its effects when it pulls on other magnets or on certain metals like iron, nickel, and cobalt. It's like a hidden force field. Every magnet has two ends, a north pole and a south pole, just like our planet Earth, which is itself a giant magnet. That's why compasses work. The needle of a compass is a tiny magnet. Its north pole is attracted to Earth's magnetic north pole, guiding explorers for centuries, and just like electric charges, magnetic poles interact. Opposite poles attract, north pulls south. Like poles repel, north pushes north away, south pushes south away. Sound familiar? Here's where it gets really interesting. Electricity and magnetism are related. They are two sides of the same coin, a cosmic duo. This was a huge discovery in the 19th century. Scientists like Hans Christian Ørsted found that an electric current, a flow of electric charges, creates a magnetic field around it. Wrap a wire around an iron nail, pass a current through the wire, and presto, you've made an electromagnet. Turn off the current and the magnetism disappears. How cool is that? And it goes the other way too. A changing magnetic field can create an electric current in a wire. This is called electromagnetic induction, discovered by Michael Faraday. This principle is the basis for almost all electricity generation. In power plants, giant magnets spin near coils of wire, or coils spin near magnets. This generates the electricity that powers our civilization. So, this deep connection between electricity and magnetism, electromagnetism, it's fundamental, it's powerful, it lights up our world. Section 6, Hot and Cold, the Universe's Energy Bill, Thermodynamics. Let's talk about energy, specifically heat energy, and how it moves and changes. This is the realm of thermodynamics, a big word, but it's about things we experience daily. Hot coffee cooling down, ice melting in your drink, the engine in your car, your own body generating heat. Thermodynamics has laws, just like Newton's laws of motion. These laws tell us how energy behaves, especially heat energy, and they are unbreakable. The universe insists. The first law of thermodynamics is also known as the law of conservation of energy. It's a simple, powerful statement. Energy cannot be created, nor can it be destroyed. It can only be converted from one form to another, or transferred from one place to another. Think about it. The chemical energy in gasoline is converted into heat energy in your car's engine, which is then converted into kinetic energy. The energy of motion. The total amount of energy stays the same, it just changes its costume. The second law of thermodynamics. This one is a bit more subtle, but just as important. It talks about entropy. Entropy is a measure of disorder, or randomness. The second law says that in any natural process, the total entropy of the universe tends to increase over time. Things naturally go from order to disorder. A neat room gets messy if you don't clean it. A hot object cools down, spreading its heat to cooler surroundings. Heat always flows from hot to cold, spontaneously, never the other way around, without help. This might sound a bit gloomy, like everything is destined to become a jumbled mess. But it's also what makes things happen. It's why engines work. They take heat from a hot source, convert some of it into work, and dump the rest into a cold sink. It's why refrigerators can keep food cold, by pumping heat out from inside, cold, to outside, warmer. But they need energy to do this. They don't violate the second law, they just move disorder around. Thermodynamics. It's the universe's accounting system for energy and change. Section 7, Weird and Wonderful, a peek into quantum physics. Now, hold on to your hats, we're diving into the quantum realm, the world of the very, very small. Atoms, electrons, photons, particles of light. Down here things get weird, really weird. The familiar rules of classical physics, Newton's laws for example, they don't quite work anymore. It's like entering a funhouse where common sense takes a holiday. But this strange world is the true foundation of reality. It's where the deepest secrets of matter and energy lie. One of the mind-bending ideas is wave-particle duality. Tiny things like electrons or photons can act like particles, little billiard balls bouncing around, but they can also act like waves, spreading out, interfering with each other, like ripples on a pond. Which one are they? Both. It depends on how you look, how you measure them. Imagine light. Sometimes it's a wave explaining how rainbows form. Sometimes it's a stream of particles explaining how solar panels work. It's a cosmic identity crisis. Another quantum puzzle is the uncertainty principle, formulated by Werner Heisenberg. It says you can't know everything about a quantum particle with perfect accuracy at the same time. For example, the more precisely you know a particle's position, the less precisely you can know its momentum, how fast it's moving, and where. And vice versa. It's not about bad measuring tools, it's a fundamental limit built into the fabric of reality. The universe has a bit of fuzziness at its core. Then there's quantization. Energy at the quantum level comes in discrete packets, or quanta. Like money comes in cents or dollars, not continuous amounts. An electron orbiting an atom can only have certain specific energy levels, like steps on a staircase. It can jump from one step to another by absorbing or emitting a quantum of energy, a photon perhaps, but it can't be steps. This idea, pioneered by Max Planck, was the birth of quantum theory. It's strange, it's counterintuitive, but it's the basis for lasers, computers, and so much modern tech. Section 8, Giants of the Cosmos, the Architects of Understanding. Physics wasn't built in a day, it's a story of brilliant minds across centuries. People driven by curiosity and a desire to understand. We've mentioned Isaac Newton. His laws of motion and gravity were like a blueprint for the cosmos for over 200 years. But the story doesn't end there. Many others have stood on his shoulders and seen even further, pushing the boundaries of knowledge, revealing more of the universe's secrets. They are the heroes of science. Then came Albert Einstein, a name synonymous with genius. In the early 20th century, he revolutionized physics, not once but twice. With his theories of relativity. Special relativity changed our ideas of space and time, showed they are intertwined, space-time, and brought us E equals mc squared, energy and mass are equivalent. Then general relativity gave us a new understanding of gravity, not as a force but as a curvature of space-time itself, caused by mass and energy. Mind blown. We must also celebrate Marie Curie, a true pioneer, in a field dominated by men. She conducted groundbreaking research on radioactivity, a term she coined. She discovered two new elements, polonium and radium. She was the first woman to win a Nobel Prize, and the only person ever to win Nobel Prizes in two different scientific fields, physics and chemistry. Her work paved the way for nuclear medicine and our understanding of the atom, an inspiration for generations, and so many others. Max Planck, who reluctantly opened the door to quantum theory. Niels Bohr, who gave us a model of the atom with electrons in specific orbits. Werner Heisenberg and his uncertainty principle. Erwin Schrödinger and his famous and perhaps unfortunate cat. Richard Feynman, a brilliant physicist and an amazing teacher, who made quantum electrodynamics understandable with quirky diagrams. These are just a few of the many architects who built our modern understanding of the physical universe. Their legacy is all around us. Section 9. From quarks to cosmos, physics shaping our world. So, what's the big deal about physics? We've journeyed from apples to atoms, from electricity to the expanding universe. Physics, at its heart, is about understanding the fundamental rules that govern everything. It's a quest for knowledge for its own sake. But it's also incredibly practical. The discoveries of physics have profoundly shaped our world, our technology, our society, and even how we see ourselves in this vast cosmic ocean. Think about the technology you use every single day. Your smartphone, full of physics, transistors, a quantum invention. GPS relies on Einstein's relativity. The internet, transmitting data as light through fiber optic cables, medical imaging, X-rays, MRI, PET scans, all born from physics research, allowing doctors to see inside us without surgery. Space exploration, rockets, satellites, all operating on principles laid down by Newton and refined by others. Physics is the engine of innovation. Beyond technology, physics changes us. It expands our horizons. It instills a sense of wonder. When you understand why the sky is blue, or how stars shine, the universe becomes even more amazing, not less. Physics teaches us a way of thinking, critical thinking, problem solving, how to ask questions, how to test ideas, how to be skeptical, but also open to new possibilities. These skills are valuable in any field of endeavor. They empower us. The journey of physics is far from over. There are still huge mysteries. Dark matter, dark energy, what are they? What happened before the Big Bang? Is there a theory of everything that can unite quantum mechanics and general relativity? The universe continues to challenge us, to beckon us forward, with its beauty, its complexity, its secrets. Physics is our tool, our guide, our spaceship. For this grand exploration, the ultimate adventure, unlocking the universe, one discovery at a time, what will we find next?